Let me recall you that we are considering Lie algebras of affine group schemes. And I simply wanted to state what I said yesterday, namely that the existence of tangent maps deduced from homomorphisms between affine group schemes. Let me simply state it. Proposition. Let H, G be affine group schemes over K. Then any any morphism from G to H provides a Lie algebra map morphism which is injective whenever G to H is the group morphism is a closed embedding. So I will not say more about this, and just simply recall you that this kind of statement can be obtained by easily by the functorial point of view, both for the underlying spaces, but also for the bracket you can compute. Okay, so now let's turn to smoothness questions. So we saw that of algebras over fields of characteristic 0 are reduced. And we want the same kind of criterion for we want a criterion for fields, whatever the characteristic of the field. And actually I'm cheating a little bit because what we will obtain is simply the fact that group scheme is reduced if and only if it is smooth in some sense. It is smooth. And this will work for algebraic schemes. Okay, so here's the criterion. What do I call it? Reducedness criterion for smoothness. here's the result. Let G be an affine group scheme which is algebraic over some field K. Then okay, let's call K bar the algebraic closure of K. Then the coordinate ring tensored by K bar is reduced if and only if we have this equality of numerical invariance. The dimension is equal to the rank of the module of differentials. Okay. So I need to explain the statement, in particular because I haven't defined the dimension yet. Okay. First, dimension of the dimension is simply, so we start with G, and we take the unit component, then we get an integral domain by modding out the coordinate ring by its radical. And the dimension, by definition, the dimension of G is the transcendence degree of a small k of the fraction field of this domain. Okay, and the second remark is that we saw yesterday that in the specific case of Hopf algebras, we can describe the module of differentials. This is precisely the coordinate ring tensored by the quotient of the augmentation ideal by its square. So if I noted that if, in particular, if K is a field, this is a vector field of over K equal to A mod I. and we get that the module of differentials is a free kg module. So the rank, in that case, so the dimension is in some sense with respect to k, and the rank is the rank at the kj module. At the kj module. Okay, so these are some explanations, some remarks now. So after this explanation, one sees that this equality expresses the smoothness at the identity element. If we want to go to, if we have want to have the viewpoint of algebraic geometry, the right-hand side of the equivalence is a smoothness at the identity element. But we saw already that we can use, okay, recall that we are dealing with groups which are homogeneous spaces under some algebraic action. So this smoothness at identity amounts to saying that we have smoothness everywhere. So this can be given a precise sense when you have to do proofs. On the algebraic side, recall that yesterday when I defined when I defined the left invariant operators on the coordinate ring of an affine group scheme, I used these translation operators, which are defined thanks to the co-multiplication delta of the Hopf algebra, and this is exactly what you can use to say that. If you want to write it properly, algebraically, that this smoothness at one point amounts to smoothness everywhere, you need to use this kind of translation operators. Wait, first, oops, yeah. Thanks. Fine. Okay. What else? So, okay, we can reformulate Cartier with these remarks. We can reformulate Cartier's theorem. Any affine group scheme over a field of characteristic 0 is smooth. Okay, so let's sketch the proof of one implication. So we may in short assume that K is algebraically closed because these invariants behave well with respect to field extensions. So assume this the coordinate ring, the tensor coordinate ring is reduced. We may shall assume that K is algebraically closed. And we can also assume that the group is connected. This is also harmless. So in this case, so then by the various connectedness criteria I gave yesterday, we deduce that K of G modulo its radical is is an integral domain. But we assume that this radical is trivial. Yeah, this is this assumption. But by assumption, this ring is simply the coordinate ring. Okay, so let's now introduce the fraction field of the ring. Okay, so we have so we go back to this the module of differentials, which is which is isomorphic to the module of differentials of this new field with respect to the base field is isomorphic to this tensor product. So the dimension, this is simply because the module of differentials behaves well with respect to localization. Therefore, the dimension of OK of this module of differential, is equal to the rank which appears in the statement. Okay, but now by the preliminary reduction, we are working over a field which is perfect because it's algebraically closed. So this implies that the extension big K over small k is separably generated. And therefore, the dimension, the transcendence degree over small k of big K is the dimension of the modular differentials, which is exactly the rank okay. And this is dimension of G by definition. Okay, so we defined Lie algebras in the previous section, and we would like to have a connection between the Lie algebra and smoothness. So here is a link connection with Lie algebras. Well, recall that we have among the various point of views on Lie algebras, we have we know that we can see the Lie algebra as the set of derivations from k derivations from the coordinate ring to k. And by definition, this is nothing else than the homomorphisms from the differentials to k. So from this, we deduce that an affine group scheme which is algebraic over some field K is smooth if and only if its dimension is equal to the dimension of the tangent space at the identity. The algebraic affine group scheme G, okay, is smooth if and only if its dimension is equal to the dimension of its Lie algebra. Okay. So now I will simply state a result saying that now we have defined the suitable objects, the suitable algebraic analogues of the usual Lie group theoretic objects. And I will state a theorem which is known as I don't know which number, an analog of Cartan's theorem, I think, saying that whenever you're dealing with a smooth group schemes, then you can decide equality of you can decide when a closed subgroup is equal to the full group. Whenever you check, whenever you have equality of the dimensions of the Lie algebras. Okay, so here's the theorem. Let G be an affine group scheme over some field K. Let H be a closed subgroup. So this is okay. So let's assume that G is connected, smooth and connected. And that H is smooth. No, sorry, proper. Is, and that H is strictly included in G. Then the dimension of H is strictly smaller than the dimension of G. Okay, so actually this proof is not specific to groups, but I'm interested in what I said before. Namely, checking equalities of group schemes when you have one inclusion and one equality at the level one equality of dimension at the level of Lie algebras. Corollary: let G, H, G, and H be as above. Assume H is smooth. Then, if the dimension of the Lie algebra of H is equal to the dimension of that of G, okay. And the last thing I would like to do, yeah? Sorry? Yeah. Okay, the last thing I would like to do is again to promote the functorial point of view on algebraic groups by mentioning a smoothness criterion in the case of in our situation. Here it is, proposition. Let G be an affine group scheme over some field K. Then G is smooth. If and only if for any K algebra R and for any ideal whose square is equal to 0, and the map from G of R to G of R mod A is surjective. Okay, this is basically what I wanted to say about smoothness. And now we turn to a topic which is natural in abstract group theory, namely, so far we have we define some notions which in some sense are it's a bit strange because we already defined the Lie algebra for an affine group scheme, but we haven't defined so far some more basic notions from group theory like quotient, kernels, and things like that. So we go back to this problem, but we have to use some technical notions from commutative algebra in order to be able to suitably define, for instance, what a quotient is for an affine group scheme. So namely, what we will do is to use the notion of faithful flatness in order to properly define the usual notions from abstract group theory, namely the quotient of a group by a normal subgroup. Okay, so our goal is to define in a suitable way quotients of affine group schemes and this requires to use faithful flatness, so I will simply recall what I need for this. Okay, so definitions. So the starting point is a ring homomorphism. We say that this homomorphism is flat. If S is flat over R, if for any injective homomorphism of R modules from M to N, the homomorphism of S modules from M tensor S to N tensor S is injective. Okay, so this is equivalent to saying that tensor product by S over R is exact. And we start with a flat morphism. Then we have equivalence between the following statements. For any R module M, if M tensor R is trivial, then M is trivial. That's the number. For any R module M, the map from the natural map from M to M tensor S is injective. And last, for any homomorphism of R modules, if the corresponding homomorphism of S modules is injective, then so is the initial homomorphism. Okay, so when these conditions hold, we say that the morphism from R to S is faithfully flat. Okay, so the point is not to study faithful flatness here, but to see how you can use how to combine the functorial point of view on algebraic groups together with this notion from commutative algebra to properly introduce quotients of affine group schemes. Okay, so let me still need to recall you some properties from of faithful flatness. Okay, so let me state it immediately. Let R to S be a faithfully flat ring homomorphism. Sorry, I forgot to say that, for instance, let's give an example. Any map from K to S with K a field is flat. And it is faithfully flat when S is non-trivial. Okay. Then we have the equivalence. Let start with a sequence of R modules, and then this sequence is exact if and only if the tensored sequence is exact. Okay, and the other point which we will, which is very useful in descent theory, is the following: let M be an R module. So we know by the, I chose to present a faithful flatness from this equivalence. We know that the map from M to M tensor S is injective. And the point is that its image oops. its image is characterized as the subset of M tensor S, on which the maps these two maps agree. Okay, so this is this is more or less what we will need, or result related to this kind of statement. Okay, I also know that when we have okay, you can say also that faithful flatness is behaves well with respect to localization and composition, but okay. I will simply mention a difficult theorem, which is a generic faithful flatness. Okay, some remarks. Good behavior. With respect to localization, composition, and moreover, there is a geometric way. If the map from R to S is flat, then faithful flatness amounts to saying that the map from spec S to spec R is surjective. Okay, so what we will use, what we want to say is that inclusions of Hopf algebras are faithfully flat. This is when the ground ring is a field, and this is proved by using a deep theorem in faithful flatness, which is a generic faithful flatness. So here it is. Let K be a field, and let A be K algebras, A and B be K algebras. Assume K is an integral domain. Sorry, A is an integral domain. Then up to localizing, the inclusion becomes faithfully flat. And then there exists such that providing faithfully flat map. So again, this is, for Hopf algebras, what we will have. So we have to localize here, but in the case of Hopf algebras, what we will be able to do is to translate the open subsets on which we have faithful flatness, and this will give a faithful flatness for the initial inclusion. That's the point. Okay, so if this is more or less as usual. It looks now usual. I introduce an algebraic notion which is very general, and in the case of Hopf algebra, this notion becomes much simpler. So up to paying the technical price to handle Hopf algebras, some general notions become more concrete in the case of Hopf algebras. In this case, this is what I said. What you have is that you have a faithful flatness for inclusions of Hopf algebras. Let K be a field and let A included in B be an injective homomorphism of Hopf algebras. Of OK. Then the inclusion is faithfully flat. Okay, so idea. So we have a generic faithful flatness plus, in this case, the possibility to translate as in smoothness considerations, or even in the definition of the algebras. The possibility to translate open subsets in order to cover the full group. Okay, so the idea is to combine. This is a difficult theorem, but the idea is to combine these two things. And now what I would like to do is to explain how to use this purely algebraic result in order to do group theory on, in order to introduce natural objects from the group theoretic point of view for affine group schemes. And in some sense, it's a bit surprising that we have to wait the use of such notions to be able to do group theory on affine group schemes. Okay, so let me turn to quotients. Okay, so here K is a field. So we want to define quotients and by the way kernels. This has not been done yet. It's easier, but much easier, but this has not been done yet. We want to define kernels and quotient for affine group schemes in such a way that classical group theoretic results hold. Like, for instance, isomorphism, the classical isomorphism theorems. Okay, so this requires some work. Okay, so let's start with two definitions, one which I have already used. So sorry, in what follows, we will use G and H, two affine group schemes. Schemes over the field K. Okay. Let phi from H to G be a homomorphism, a natural transformation from H to G. So let me recall you that we say that phi is a closed embedding if the map, if the comorphism from between the coordinate rings is surjective. So I recall the definition because it's completely, the next one, which is new, is completely, in some sense, complementary with respect to factorization. We say that phi is a quotient map if the comorphism is injective. So the Zariski, the intuition for Zariski topology more or less says that being a quotient map is related to the fact that you have a dense image, which is the case if you're dealing with algebraic group schemes. Okay, so by passing to comorphisms, with this term, it's just a point of terminology. It's easy to see that any homomorphism between affine group schemes can be factored as a quotient map composed with a closed embedding. So any homomorphism between affine group schemes is the composition of a quotient map and a closed embedding. Just by the corresponding factorization. This is terminology, factorization of comorphisms plus terminology. Okay, so now let me state a lemma, which is the first, in order to, as soon as possible, illustrate the use of faithful flatness. Let me state the following lemma. Let phi from H to G be a quotient map. As above. Assume that for any key algebra R, the map phi R between the R points is injective. Then phi is an automorphism. Of affine group schemes. Okay. So let's prove it. So we have a So we have a comorphism which is injective by assumption. Okay, we started with a quotient map. And the idea, the trick is to use faithful flatness. So the trick which follows is in principle not so surprising. Idea, trick. Use the maps from KH the first map goes from attaches to x, one tensor x, the other one attaches the other tensor. Okay, so what is it? But we can see these maps as points of H evaluated on this key algebra. Okay, we can see these maps as points in in H of this strange key algebra. Okay, but this is R, if you want. But what is if we precompose by phi? We see that. So what is precomposing by phi? It's simply going to G over the same map, over G of the same ring. Okay, you see that. Precomposing by phi. By yeah, okay, by phi star. Okay, but by assumption, but by definition of this tensor product, the points have the same image. Okay, simply because we tensor over K over G, so you can put it. Elements of K over G can be on whatever side. Okay, but the image of the 2 points, the two previous points, in G of R are the same. So the second assumption, which is that this map is injective for any R, so in particular for this K algebra, this ad hoc K algebra. From this we can conclude, so they are the same. They are the same already in H of R by the injectivity assumption. So this means that these 2 points lie. So this means that, sorry, the image of the image of this map sorry. Okay, this is where I use faithful flatness, but by is faithfully flat. So that so that's the subset of on which the subset of K of H on which these maps agree. On which is what did I want? Sorry. What do I want to say? The subset of K of H. Sorry, on which the two maps agree is K of G. And this implies that this map is an automorphism. Okay. Okay, so what is the consequence of this lemma? By factorizing we see that homomorphism from H to G as above is a closed embedding if and only if we can check injectivity for any key algebra. So instead of checking, it's now instead of always stating things by involving checking injectivity for each key algebra, we can simply introduce the kernel of a map between fine group schemes. Okay. So the kernel, let phi be as before. The kernel of phi is the group functor which to each key algebra R attaches the kernel of phi R. And actually, it turns out that this is an affine group scheme. Because the trick is to see this kernel as the fiber product of the injection of the trivial group in G and the map phi. Okay, so the kernel can be seen as a fiber product, and this fiber one can check that this fiber product is represented by this key algebra. So this is the augmentation ideal of G, and this is isomorphic to this quotient. Okay, so with this terminology at hand, we can reformulate the previous consequence by saying that a homomorphism between affine group schemes with trivial kernel is a closed embedding. Okay, so the first. So this is simply a reformulation of the consequence. And now, what I would like to do is to state the universal property of quotients. We also have a universal property for quotient. Here it is. Let phi from H to G be a quotient map. Then any homomorphism. Okay, let me check. Any homomorphism from H, say to H prime, vanishing on the kernel of phi factors through phi. Okay, so you have to, this is something which is completely standard in abstract group theory, and it is not obvious in this context. Okay, so what's the idea of proof? The idea is to consider the maps you again consider this fiber product to which are associated two projections. Okay, and okay. No, sorry. It's okay. Sorry, I should have read my notes. We are considering a fiber product of a group. Sorry. Yeah. Okay. This at least there is this. We have at least here a group theoretic intuition. Okay, we are considering these maps. We are considering these maps, and we push further to H prime. And what does it mean that this map vanishing on the kernel of H? It means that okay, we have a comorphism map. Okay, with this usual key algebra, we can again consider. We have two projections here. And what does it mean to be, if we assume that the homomorphism vanishes on the kernel of phi, it simply means that these two projections agree. Okay, the assumption implies that the two projections agree. Okay, so it means that this map lies. The image of this map lies in the equalizer of these two maps. Homomorphism. And again, by faithful flatness, this implies that this map actually goes to by faithful flatness. This equalizer is equal to k of j. So we obtain the factorization. Okay. So one thing that is left to do is to say that quotient do exist, which is not clear so far, and actually it's a difficult thing to do, to prove the existence of a quotient. And the idea is to go, in some sense, the idea is to go back to Chevalet's theorem, which tells you that any affine algebraic, if you start with recall that if you start with an affine group scheme, and if you assume the finiteness assumption that it is algebraic over some field, then you can embed it as a matrix group. Then you go back to this theorem, but you prove a more precise version of this. You prove the existence. So now you are given an affine group scheme, but also a subgroup. So what you want is a linear representation in which you will have a line whose stabilizer is precisely the closed subgroup you started with. And then the idea is to follow the orbit of this line to obtain the quotient of an affine group scheme by a closed subgroup. Okay, and in the case which was considered today, where we have a normal subgroup, then you obtain again an affine group scheme. But if you start with not necessarily normal closed subgroup, then what you obtain is simply a variety, which is useless in the theory of algebraic groups, because a remarkable class of subgroups for a given algebraic group is a class of parabolic subgroups, namely the subgroups for which this quotient variety is complete. Is a complete one. Okay, so I plan tomorrow to introduce classes of remarkable subgroups and the corresponding conjugacy statements. And I'm not sure I will be able to say much about the structure of reductive groups.